So let's get started. If I counted correctly, we've now 5 weeks left of the semester.
I didn't die yet. Wow.
Yeah, but the hardest part is coming up.
Right.
And so we have, of course, next week is broken up because it's Thanksgiving, right? I wanted to start doing Spark streaming today, but there's some startup time, so I wasn't quite ready. So we'll talk about some other things. The problem with streaming, Spark streaming, is you need a source to stream, to have a stream. And so to do that, we'll use Kafka. And so we have to go back to look at Kafka, which involves more installing, which we'll see how many Windows machines that breaks. And once we get Kafka, we give a source, and we can go back and look at streaming on Spark. We also have to worry about projects. So hopefully you've been thinking about that. So what I'm thinking of doing is, since next week is sort of broken up, is have a class period where people talk about what they're thinking about doing their projects, right? So for a week from today, he's going to give us a great idea for a project, right? Good. Any questions?
With the idea for this project, I guess how complex is
Well, I have not done projects in this class before, so I don't have any previous students to say, here's the, they should be a bit more substantial than the assignments. So one thing, so my other class I'm teaching iOS development, and so I'm going to talk about Apple's MLKit. So I spent all weekend playing around with that, and that sort of ties into today's lecture. So initially I wanted to start, well, I need to close this. I wanted to look at clustering, but I got to thinking about, I got slightly sidetracked. So last week there was this XHCD comic. So some of you probably have no idea what it's about. It turns out that in Apple iOS, you've got a keyboard, and the keyboard will suggest, as you type, it suggests words. Initially, that was just sort of dictionary lookup, right? You type in a few letters, and it suggests what words make. But they now use machine learning to suggest the words, right? And actually, I use that on this computer. You got this silly touch bar, and it turns out that the operating systems look at what you've been reading and uses that context to figure out what words to suggest. And what happened is, for somehow the algorithm learned that in certain contexts, when you type I, it should it would return A, then a question mark, which is like, the internet really loved that. Oh, look at that. but it shows that, we've got a keyboard that's powered by machine learning, right? And so they got this Apple MLKit. It runs, on Mac OS, iOS. It runs on a watch, right? And the interesting thing was, when you actually look at the kit, right, and what it does, once you have the model, right, once you've trained your model, whatever it is, to actually use it, it's like two lines. You create the model object, and then you call a method on it, and you give it the input, and it gives you answers back. That's it. But that's the same thing in Spark, right? Once you've trained the model, it's just basically one line. Once you've fitted it or trained it, you just call one method to say, here's my input, tell me the answer, right? And so once you've trained your model, and you can in Spark, you can save it later on. You can read it back again and say, okay, here's more data. Tell me the answer, right? And then yesterday at a medical conference, some people from UCSF and a startup company. I don't know the background. It's probably some smart guys from UCSF and Stanford, someplace, started a startup company. What they did is they had a bunch of people, and they started with 6,000 people in the test. They gave them Apple Watches, and they wore them from 1 to 50 weeks, and then they actually, measured them medically with the proper equipment. Took all that data, formed a training set with 70% of them right, and 30% were test data, and they were looking for various types of things. Earlier, they said that 97% of the time they can detect using the watch irregular heartbeats, which can lead to other complications. Yesterday, they announced that with 82% accuracy, they were able to detect hypertension in people. And 90% of the time, 90% accurate sleep apnea. This is a presentation, a conference, so they didn't have a paper, so I couldn't read the paper to see what they mean by 82% accuracy. I mean, they're talking false positives, false negatives, true negatives, right? Don't know. But also medical people, so who knows what it means. Other studies, a lot of this started last year. Google researchers published a paper on using and how do they do this? Right? There's a deep learning algorithm called DeepHeart they used, right? So all they're doing is gathering all this data, right? Measuring, whatever, wherever the watch measures, usually it's just heartbeats, right? And they're taking that data, and they're taking all the tests on the people that figure out the blood pressure, blah, blah, right? And they're just feeding it in to this machine learning algorithm. That's it. That's all they're doing. And once they've got the model right, it's really the point now where if they hand the model to me, I could go to my next class and say, here's your model, write me an application, right, to use it. And it started, last year, Google published a paper on detecting diabetic eye disease. Again, it's all machine learning, right? It's not. And then earlier this year, Stanford published a paper on, deep learning algorithm to identify skin cancer, and it does as well as a dermatologist, right? It's machine learning. And then last week, I'm not sure I can pronounce this right. Is anyone probably Eastern European? Andridge, or maybe he's Indian, I don't know. He's the director of AI at Tesla, which I'm sure presumably everyone knows what Tesla is. He wrote this article called Software 2.0. And so Software 1.0 is, it's writing code in whatever language you're using now, right? The Software 2 is training neural networks, right? You don't write code, right? Someone writes the neural networks, right? Someone designed the networks, and you pick the one you want to use. And like the guys in the study, they just input the data, right? Like your previous assignment, or your current assignment, here's the data, here's my decision tree forest. I input the data, it trains it. Now here's my test set. I run it, right? And he says, look, we're not going to replace Software 1.0, but more and more things you'll do with neural networks. You want to recognize images. No one does that by hand anymore, right? It's not done by hand. You use a neural network, right? Speech recognition. That was, people have been working on that problem for, speech assist, machine translation takes one text and translates from one language to another text. People working on that for decades, right? This goes back to the 60s. Noam Chomsky was this famous linguist. He does all this work and studying how the brain operates and what machinery is there. And he actually, there's some results you'll study, right, in either automata theory or formal languages that are from him, because he was trying to understand how to parse natural languages so we can recognize them. And linguists built these huge, complicated models of going into the syntax of language, the semantics of language. And at one point, Google said, well, we'll just go over and just sort of copy all the books in the library and look at all the ones that are written in English and in French and English and Spanish, and we'll just feed into a machine learning algorithm. And it blew everyone away. I mean, it was more accurate than the models that linguists were spending decades producing, right? People don't write hand code anymore based on structures of language and syntax. It's all just machine learning, right? And it says in robotics, it's not there yet, but people are working on it, getting close. In games, well, we know that chess has been conquered, right? What's that? And then Go has been beaten, right? And he says, yeah, the benefits of this are, neural networks are just basically matrix operations and, doing cutoffs, right? So there are very few operations you have to worry about, which makes it easy to build it in silicon. You can actually build chips that do neural networks. And Google does this, Facebook does this, Amazon does this, right? Their clusters now all have special purpose hardware just to neural networks, right? To make it fast. You don't have to worry about, worst case, best case, because it doesn't matter if you're doing image recognition. It takes the same amount of time with a complicated picture or a simple picture, because it's just sending the same bits through this neural network. End of story, right? You know how much memory it's going to use? Again, it doesn't matter what the image is. It's the same bits. Portable, we can swap it from different models, different machines. If it's too slow, you can reduce the number of layers in a neural network to make it faster. If you want more accuracy, just add more data and train it better, right? And it says, in all these areas, forget it. You're not going to be able to write a program that can perform better than these neural networks, right? You're not going to write a Go program that can beat, right, the neural networks that do play Go. You're not going to be able to write a machine translation program that can beat Google's AI at machine translation. Just you won't. Now, there are some problems, right? Because what you're doing, you're training the model, and you know that there can be some times when it's going to be wrong on some pieces, right? You can't get a perfect model, and it can do weird things. Last year Microsoft had this bot, and it turned into a Nazi, right? And it was spouting, white supremacist stuff, right? And they had to unplug it. They had to bring it down. And then Apple had this problem, right, with the keyboard. Did weird things. And now, what that article didn't talk about is there's actually a business advantage to doing this too. The iPhone came out the next day, right? The Android team's like, we're wrong, they're right. We need to redo things, right? Because Android was originally written to use a screen, the 3 or 4 lines long, which is very common at that time, right? And they realized, no, wrong. It took Apple, how many years of planning, experimenting, and trying this and trying that, et cetera, to realize, oh, we can use the whole screen. Here's how we do it, right? And they figured all these details, and the next day, everyone in the world can say, yep, that's the way to do it. Thank you, Apple. You just saved us $5 million in research, right? Steve Jobs was furious, right? He was just furious at Google and went on a warpath for him because, like, you're stealing our ideas. And like, well, yeah, sure. Everyone does that, right? And Samsung is famous for this. They copy things all the time. And it's sort of easy to copy hardware, right? But you see it, okay, yes, that's a good idea. Now let's figure out how we can do it. Amazon Alexa, oh, all of a sudden, Google comes out with their, Apple's coming out with theirs, right? Once you got the idea, once you get the hardware is not that hard, right? You need a speaker, you need a microphone, right? Oh, you need a good microphone. But in the software 2 stuff, the algorithms are there. Everyone knows what the algorithms are, right? You can go online and here's the algorithm you want to use. But you need the data, right? It doesn't help us to know which machine learning algorithm Google used to do machine translation. Why? Well, because you need all those texts, right? Translated in 2 different languages, so we can train that algorithm. We can train that neural network. So some people are saying, yeah, this is the way Google and Apple are now going to try and differentiate their platforms by using AI, right, on the data they have that other people don't. Anyone hear of Bixby? What's that?
It's capable of really like high-end command processing, but it sometimes doesn't have the same speed.
Right, and it doesn't have the same functionality, right?
Yeah.
Doesn't come from Google. It comes from Samsung.
Yeah.
And the problem is Samsung does not have the data that Google does, right? They've got years of voice, and they've marked it all up, and so they can train it, so they can recognize it more. They know what types of commands people want to use, right? Because they've been doing Google search for a long time. They have all the searches, and now you can actually talk to it, right? And so they've got years of people asking questions, right? It's the data. So we're in a new era, right? This is, we're now seeing phones. It's now possible for students to write applications using machine learning on phones. Right. Earlier, the Magic Sudoku I was showing before class, the company was like, "Oh, Apple has this new machine learning kit. Let's try it out." Right. And then they also use their VR kit to show it like it was on their page. Right. So, these things are not possible. Right. In your assignments, we had some, small data sets to train various little things, right? But it turns out that you can actually export those models. Unfortunately, Spark doesn't support it on the ML side, only on the MLlib side. And they export it to this PMML language. So you can actually train things using Spark and export it, and then import it to another library, and then so you can create a model and embed it in an application. One of the differences between Spark and things like R and what you do in Python is Spark is mainly an infrastructure issue, right? It's mainly, their main goal was to allow you to do things on a cluster. And so a lot of the work they do with cluster management and redundancy, dealing with distributed file systems, managing batch jobs, that sort of stuff. So they're not up to speed on importing, exporting, and using those models elsewhere. But so their old ML library does do some of it. And this PMML is a predictive model markup language. And if you want to look at various ML libraries and who supports what, there's a URL, a fairly comprehensive list. But for me, it's like, the Industrial Revolution, right? And everyone was a farmer, and then didn't have a hand. All of a sudden, people said, "Oh, we can use steam engines and all this." We can actually use machines to do things, and it completely changed the world, right? And we're seeing more and more of that now. The machine learning stuff is just one of these things which are going to happen, which are going to transform not only the world in general, but how you people will be dealing with things professionally. It's not to say that regular programming will go away. It's just that more and more tasks, right, will be done with machine learning. How do you deal with all the sensor stuff people wear? I mean, use machine learning to diagnose people's problems, right? It's going to be much easier to do that than it is to figure out, the causal relationship of all the good blood pressure and have people come in and measure. No, I just do machine learning, right? And I would expect a lot of that to start happening in San Diego because San Diego is a big place for biotech startup companies. So enough soapbox. There are a couple of things I want to talk about in terms of sort of machine learning. One is clustering, and the other one is neural networks. Spark does not support implement a neural network library. So later, after we talk about streaming, I may come back to it. We'll see. Clustering is an unsupervised machine learning algorithm, so you don't have to train it. You just here's my data, make it a cluster, and then it figures it out. And there's lots of uses for it. Bioinformatics, marketing, researchers like figure out what type of customer are you, so how can we sell things to you. A lot of recommender systems use it in terms of trying to figure out what type of group you're in, so it can recommend what sort of music you might like. So Last.fm, Netflix, recommendations. And so this is basically a group data based on distance. What data is close to each other? And then what do we mean by distance? In an Amazon case, we're looking at what people bought, right, or looked at. So how do you then measure that as distance? Well, you create this huge n-dimensional space where dimension might be a particular type of product or a product. But it turns out there's, we're used to thinking distance as well. I start here and I end up there, and so I can then just measure it, right? But there's all kinds of ways we can actually look at measuring distance. Some examples, right? You have a two-dimensional grid. Euclidean distance is what we just know, you draw a line, you take a ruler and say, oh, that's how far it is. A city block is, well, it's like how many blocks do you have to go? And you can't go diagonally, so you can go down, 1 unit, that's 1 block, another block, another block, another block. So it's 4 blocks away, right? Hamming distance. Has anyone studied Hamming distance? Yeah, right. I mean, usually it's 2 codes, right? You want to know, or 2 bit sequences. You want to know how many bits do you have to flip to convert one into the other, right? That's a form of distance, right? Cosine distance is often used in language. You have 2 points in the plane, you zero them, and then see the cosine distance. There's all kinds of different distances we can use. Now, again, Spark is right. It's primarily an infrastructure issue. It's not like other systems that were designed to do data science, right? So Spark doesn't support different types of distances. You have to do that yourself before you submit. You have to transform it, right? Whatever distance you want. If we're in Python or Julia, you have to have a library that says, okay, you want Euclidean distance, okay, here's what it is. Or you want Hamming distance, here's a function you call. In Spark, you get to write your own. And the problem is if you're dealing with distance, the scale, are you talking inches? Are you talking feet? What scale you use can affect things. Particularly if it's just physical distance, it's not going to matter. But if we're talking a number of different types of units, right? Because we're trying to encapsulate, looking at medical data, it's not all, it's going to be some blood pressure and some, temperature, etc., various other measurements, and so different units of different types. So the way of actually normalizing them in some way, min, max, well, you just map things to 0, 1. So here's an example, right? Here's my data, and I can just, the minimum one goes to 0, the maximum goes to 1, and then you scale those, right? Of course, the problem is, if you've got a really large number, what does that do? Well, all these numbers get squashed down into a real small range, right? And so then everything becomes really close, and then you got that one monster over there. That can cause problems, right? The standard deviation, pretty much everything between -3 and 3. And if you got outliers, really big numbers, it's not quite as bad, right, as doing 0, 1. The sigmoid, again, it goes to range 0 to 1. When you get larger numbers, what happens is those outliers just get mapped to the biggest value. And basically what you're doing is you're doing something like this, right? And then you can sort of scale it to figure out. And that's basically a particular instance of what they call a logistic function. And this is used a lot in neural networks. Why? Because each neuron has to figure out when to fire or not. And you don't know how large a range of data is going to be. And so this takes care of, you can then figure out, okay, when things get too large, I'm going to ignore it because it's going to swamp all my data. And so at some point, you pick off how slow you want to slope off. At some point, it just maps everything to the same value to knock off the effect of all these outliers. And also, if you're a sports fan, anyone heard of the ELO system of ranking teams, players? Apparently, there's no sports fans. Too nerdy, huh? What's that? And again, it's basically, outliers just get mapped to that top value. And we can pick different ranges, right, to deal with how far we want that cutoff to occur. And this is one of the things when you train neural networks, is one hyperparameter to figure out, what cutoff values you want to use. Different examples of and again, a similar one, Softmax Normalization, very similar. But the idea is that we have to worry about what distance measure we're going to use, and we have to worry, we have to normalize the data so we're not exaggerating things. In text, right? If we're dealing with text and you want to model text, we also may want to know a form of distance. And the problem with that is How do you do that, particularly since words are different, right? And we can, you take something, I'm taking something, but that's the same word. You get lots of punctuation marks, a lot of crazy things, a lot of words which don't matter much. I mean, the and they don't provide any context. And so typically, when you deal with text, you want some sort of system to strip out all the punctuation you don't need, strip out all irrelevant words, and then find the stem words. So we're not taking words which have the same, basically the same word with different endings and treat them differently. And then people create different metrics for how can we measure distance in text, right? So one way is to think of text as sets, and Jaccard index is you have two sets, and you look at the union, the intersection, and that gives you a measure of distance between those two sets. And then if you want distance, right, we can subtract it from one. You know, some phrases, and then measuring the Jaccard distance from A and B. Well, you have is the of, right, in common. And so we're getting things looking for similar because we have too many common words, right? Which don't mean anything. You really want music, food, love. So you'd expect A and C to be far more similar than A and B, right? Because B is talking about war, and when we normalize the text, right, then the distances A and B are much farther apart than A and C. So there are ways of actually measuring distance between text. Um, um, another way of doing it is you take a piece of text and you treat it as a vector, and each word becomes a different dimension, and so you then create a huge n-dimensional space, right? And each a sentence is it going to be a vector pointing to some, and then you can use that the cosine of the distance of those vectors as a form of distance between, and then we can start doing clustering on text. All right, so example doing that, here we go. Take the same sentences, strip out the word, right? And then look at the root words, and then music becomes, food is mentioned one, history is mentioned two, right? And so that is just that vector. And then another vector, another vector. Now we can start asking how far apart are those vectors, right? And use that as a distance measure for text. And yes, you get a very high dimensional space. And then we can use cosine distance to and doing that, and these two, the cosine distance is 1. When music, food, love versus love, music, right, the distance is much closer. All right, and those are the vectors. So to do clustering, we need to know about distance. Remember about distance, we know what type of distance we're talking about, and we also wrote normalization. And the weird thing is that we can take text and take words and get a measure of how far apart they are, how close they are together. So we can do clustering on text. There are a number of common clustering algorithms. The k-means and k-nearest neighbor are probably the most common. Spark implements the k-means clustering. The algorithm is very simple-minded, almost the point of, can this really work? What you do is you basically take, first of all, in clustering, you have to decide in advance how many clusters you think you're going to be. I think there are going to be 3 clusters. And then you pick 3 random data points. And you say, okay, those are going to be my starting points. And now I'm going to divide my data into clusters based on those 3 points. And you pick a point from your data, and you see which point is closest to, and you add to that cluster, right? And then you do that for all the data points. And then when you're done, you take your, in this case, 3 clusters and find the median, right, value of each cluster. And that becomes your new median. And then you figure out, you reassign all the points to those new clusters. And if it changes points, you do it again, right? And then you find the median of those new clusters and then reassign points. If they change, if any point changes, you can do it again and again and again until things settle down. That's it. It does matter where you seed your points, right? And picking different starting points can lead you to different ending points. And so one thing you might end up doing is, repeating the process multiple times with different starting points to see which clusters seem better to you. So here's an example, some data points, and then the 3 clusters, the colored ones are the ones we're picked for the, right? And then you break it into which points are closest to each point, right? And then once you've done that, you then figure out the new means of those clusters, and then you repeat the process and redistribute, and you keep on going until you're done, right? So a simple example, the R data set has this X Clara. I have no idea where the name comes from. It's made up data. And here's the data being plotted. And so there's obviously 3 main clusters, and then there's a few points to sort of get in the boundary. Right? And when I ran it with 3, saying I want 3 clusters, here's what I got, right? And it makes sense, right? Because, all these things are clear together. Now, it becomes interesting in what happens in this boundary, right? Should this guy be here, right? Or should it be there? Yeah, it could be either, right? So maybe if I started with different, ran it again, so different starting points, that one may have gone here. This one looks like maybe it should really be here, but it's still far from the center. Some of these people could probably change, right? Here, it's, these, that guy is probably also iffy, right?
So you're graph your dimensions.
Yes. This data is two-dimensional, right? And that leaves an interesting problem. Most of the time when you're doing clustering, it's not going to be two-dimensional. And so graphing like this, on this data set, we really don't need an algorithm to tell us where the clusters are, right? We can just plot it like this, and except for a few of those boundary points, it's clear where they belong. And here is the problem. A hyperparameter to a clustering algorithm is the number of clusters you think there's in the data. This case, we know the answer in advance, right? It's 3. If you've got n-dimensional data, how do we know in advance how many clusters there should be? Right? And there are a number of issues. On that data set, both dimensions were just numeric, right? Distance, right? Standard values 0 through n. When we're dealing with other data, they may be completely different units. Blood pressure, temperature, right? Age, sex. And picking the initial mean, so we can sort of solve that one by running it n times and picking different ones, right? Picking the number of clusters becomes a challenge, right? How do we know how many clusters there should be? And then once we figure out how many clusters we want, different starting points need different answers. How do we know which clusters would be better? And I did it, right? Same data set, 2, right? Well, you said you wanted 2, so it gave me red, red. But then you get some weird things like, well, this blue, right? You say, no, that clearly belongs here, but the center of this cluster is now like over here, right? And the center is here, so it's becoming. And then when you go above the natural number, well, it just sliced the one in half, right? In some weird way. Why not like that? I don't know. I mean, again, you pick something and it just keeps on doing it until things stop shifting around. 5, again, this one was sliced this way, right? When I did 5, it was sliced like that. And then this one was sliced like that. We can tell the algorithm any number we want, and it will give us an answer. And this time it's slice them in 1/3, right? Now, so the plots were not done clearly not done with Spark, right? In Spark, here's a data set. The ML library has a k-means, it has some other clustering algorithms. You need to set the number of clusters and a seed to set the random number generator that picks it right where we start. Here it is, a complete program in Spark, right, to do clustering. It's just, first part is here's my schema to read it. I'm reading the data. I need to convert the data into a vector, right? So up to here, all this is just reading the data and formatting it for us, right? And then it's create a cluster object and fit it. That's it. So again, it's just 2 lines, right? And then I just copied the examples I gave, and so they could they do this compute cost, right? And print it out, and then you can print out the centers. Again, the fact that Spark is mainly an infrastructure problem, not a data science project per se. In other libraries, when you create a cluster, you can say, show me all the points in this cluster, right? So you can see what goes in there. Spark doesn't do that. They say, here's the centers. And if you want to know what points are in there, you write some more code to say, tell me what, this point is closest to which of those centers, right? And then it'll tell you you compute what cluster it's in. It's not that hard, right? It's just data point, 3 data points, which one's closer? You could all do this, right? Shouldn't take you longer than half hour, right? Just to write a little loop and say, distance here, distance here, distance there. So it goes in this cluster, right? So again, at this point, running the code is like, yeah. The question is, what format does the data have to be in, right? And what function do I call? And there's my model. We don't need to know how the algorithm works, right? It's helpful to understand so we know what's going on. And here's the output, right? So it gave me the sum of the squared errors, and then the cluster points. And again, this clustering algorithm computes in basically the middle of each cluster, right? So you get these crazy, whenever I see a number like that, I just go, oh, come on, guys. Don't be stupid. Why are you doing that? You really think your data is that accurate? No, I don't think so. All right. So for me, it's like, oh, people are using the classifiers, right? How do we do that? Right? How do we actually, once we've got a cluster, how do we use it as a classifier? Right? Well, in this example, the data was made up, right? But in other cases, it'll be real data and it has a meaning, right? So in the dealing with hypertension, you can have various measurements, right? You can have the input from the watch, and you can have the, various parameters, and one of them is going to be you actually measure their blood pressure, right? And so then you can label that as this guy is hypertensive, right? This one is not hypertensive, right? And so all your training data is going to have that label, right? And so when you look at the clusters, you now look at that cluster and say, look, what is this cluster, right? And you can go look at the data in there and see what property it's separating out. So let me know, this is hypertensive, this is low, low blood pressure, this is medium blood pressure, right? And once you've identified that, then do the classifier. So it's like, okay, I now know what each one of those clusters represents. It may take some figuring out because you might, if you've got 10 clusters in an n-dimensional space, well, it's going to take some doing, right? And then you just, when you have a new data point, you just, which point is it closer to? Which cluster does it belong to? And then we know what that cluster represents. So you're hypertensive. Oh, you're a sports person. You like sports gear. So we're going to recommend, oh, you're a football player. Okay, you like football. So we're going to recommend these football gear, right? Any questions? Um, syllabus, it's a method for validating a cluster of data. So there are various metrics that people propose to sort of measure how good a cluster is. This is one of them. If this value is close to 1, then the cluster, that point is close to the cluster, is well within it. If it's close to -1, then there's a problem. And then you can start probing and look at the values and playing around. And I did look at, that within set sum of squared errors that the Spark cluster model produces, and you definitely cannot use it to figure out how many clusters to use. Why? Well, because the more clusters you use, the lower the value. End of story. Why? Well, because what are you doing? You're computing you look at, here's the center, here's my point. I take that distance and I square it, right? And then I sum it up over all the points in the cluster. The more clusters you have, the closer they're going to be together, right? So the distance will be, right? So when I did 1,000 clusters, it's really small because clusters are going to be very tight. And presumably, I think there was like 2,000 data points. So if I did 2,000 clusters, it should be like 1, because each point becomes its own cluster. Now, it might make sense if I think there's going to be n clusters, and I do it k times in different results, and then this value might help us determine between this, there's the same number of clusters. And then what happens when you've got a dataset like this, right? It is made up. I made it up to fool the algorithm. But clearly, if it's doing clustering here, there's two clusters, right? The inner one and the outer one. But no, when you do the clustering algorithm, it splits it in half. Of course, if I did it again, it might split it in half different ways, right? Why? Because it's trying to pick a point, right? And then center around that point. There are different clustering algorithms we can use to deal with this problem. But it's like all machine learning is that there's always going to be patterns that they can't handle.
This type of are the number of big.
Can you have a big cluster and small cluster? If we did this different algorithm, we'd have that cluster and this cluster, right? And so small, big, right? And you'd expect that most of the time, right? In the case of medical data, I mean, you'd expect most people to be relatively healthy, right? And then there's going to be lots of people close to normal, and then people really sick are going to be outliers, right? On Amazon, right? There are certain things which are very common that people, a lot of people are interested in buying, and then there's always people interested in weirdo things, right? Unusual things. Music, I mean, is everyone interested in the same sort of music? Well, no, there's a big population that's interested in popular music. But then there's going to be a few people who are interested in French Baroque music, right? And they're going to be outliers. And so they'll be smaller clusters. And the problem here is that, the K-clustering assumes that clusters are convex, right? And centered around a point. If clusters are somehow odd shape, right, it's not going to do well. And any sort of algorithm which is trying to maximize something usually has this problem of local maximum minimum, right? And so, the standard thing we talk about greedy algorithms, like if I start here and I want to maximize values, I'm going to march up, right? Until I get to the top. It's like, well, now what do I do? The algorithm says, be greedy and go whichever direction gives you a better value, and you get stuck there, right? And you never jump over here. And so the typical solution to that is you run the algorithm multiple times, but you don't always start at the same point, right? And then you check the results and see. So in this case, you pick different initial seeds, right, and try and figure out. Right? Now I'm reminded of, well, I don't know if it's a famous experiment, but it was an interesting experiment that some psychologists did. And what they did is they use students in a classroom, but the students were not the subject. The professor was the subject, the instructor was the subject. And so what they did is, and they did tell the instructor this, right? That they told the students, look, whenever the instructor goes to, say, the left side of the room, act interested. And whenever you go, he goes to the other side of the room, just act uninterested, don't answer any questions, do something else, right? You know what the result of the experiment was? He was, by the end of class, he was like over here. And, and it was just, it was interesting, right? The students just being able to, just subtly act more interested, less interested. They drove the instructor, they could drive him to one side of the room, right? What's that? I didn't actually read the real reports that it may have, but I just heard it secondhand that they did an experiment and they were able to. So what's happened is, you people have trained me, right? Well, actually, both sides of the room have trained me because they never ask any questions, right? They're always like, and these people are like, oh, much well they say something, so I'm always going like this, right? Right.
So you've been testing us to see if it works still.
Oh, it always works, right? Yeah. So my goal is on Thursday to talk about Kafka. We'll see how it goes. It takes a lot of time to prepare a lecture on new material that I don't know yet. So there's only 1.5 days between now and then. If there are no questions, we'll adjourn for the day.
So this last slide, try multiple times before the are you just counting on getting for one class? Is there any way to get the best?
Yeah, you want some way of measuring whether the results are good or not, and then you do it multiple times and then pick the best one. It's a common process in optimization is, there's going to be local maximum or minimum, and so you try it multiple times, and there's other algorithms to try that different ways, but yeah.